Welcome everyone to Down the Rabbit Hole. This is a meetup about distributed systems at the Venmo office in New York. We do it about every 3 to 4 weeks. A bunch of people come together and we have some pizza and refreshments and we talk about distributed systems. Generally the format is some lecture of some kind, and it's put together by the study groups that are in between the talk meetups. I'm Andrew Kelleher. I'm a staff engineer and data architect over at Venmo. I work on a lot of distributed systems, and I'm primarily interested in scaling the ones that are rate heavy. So I get a lot of practice with this sort of thing. Today we're going to go over what is a bottleneck. We'll talk about a common definition and discuss a more formal definition. We'll talk about what a resource is, because when we're talking about bottlenecks, we need some kind of a resource that is bottlenecking us. It's a finite, so our resources that we're interested in are finite quantities, and they correspond to an idea of headroom, which is colloquial, but we'll define it for the sake of discussion. Then we'll talk about resources as a limiting reactant, like in some kind of chemical reaction. Next, we'll move into a section on bottleneck detection. So once you're in a bottleneck, once you have a system that's hit its limit, how do you figure that out? How do you find that? What are the characteristics? And then we'll get into prediction. So I have a system that's working fine, and I don't have a load test environment necessarily, or maybe I do. It doesn't really matter, because I can look at the data that I have about my environment and determine whether it's going to bottleneck and when, and what component is going to bottleneck it. And from there, I can provision more resources as necessary. Now, before provisioning those resources, it's important to make some considerations. So that'll be our last section. And the biggest one that comes to mind for most people is the downstream effects of scaling. And we'll touch on nonlinearities, because that's also an important factor, and it can have some impacts if you're not really sure about it. Okay, so let's get on the same page. What is a bottleneck? The common definition is from the perspective of a process. So this is some process in a chain of processes that cause our overall system to be limited. Now, in this meetup, we're going to talk about bottlenecks in terms of resources. So that's something that might be a departure from what you're used to, but it works well this way, and you'll see why later. But for the sake of discussion, a bottleneck is a resource in this talk, as opposed to a process under the common definition. So more rigorous definition, that's what the whole rest of this presentation is about. And so we're going to get into that, and we'll start with defining what a resource is, because again, this is bottlenecks from the perspective of resources. So a resource, for the sake of this discussion, is something limited, something that we don't have infinite of. So CPU, memory, disk I/O, network bandwidth, disk space, RAM, space and RAM, memory. These are all examples of limited resources that can cause our systems to bottleneck. So you can think of all of those resources as some kind of a vector, where R0, R1 up to Rn is some quantity of a resource. So for example, we can have 1 second of CPU time over the course of a second. Or we can have 2 seconds of CPU time in the case that we have 2 cores on that machine. We can have 16 gigs of RAM. So this isn't really constraining our units or our magnitude of resources. It's just specifying that we have some vector of resources, and R is less than infinity, so it's limited. So now you can think of headroom as whatever the rest is some kind of maximum value compared to R. So if we have a 16 gigabyte box, then our amount of resources being consumed, our R, might be 8 gigabytes, and our H might be 16 gigabytes. So R is strictly less than or equal to H for each element of H. And that's an important consideration, because it means that we're able to quantify what sort of all of our resources combined are, all of the limitations that we have on the system as a whole. So let's define our quantity R prime, where Ri is over Rh for every R in R and H in H. So this is a funny looking equation, but basically we're defining a new vector where R is where each element of R prime is the percent of total resources that we're consuming. So again, H is the maximum available, and R is what we're consuming at any given time, or at the current time. And R prime is the percentage of the total resources that we're consuming. So this is our definition of our resource consumption. We're interested in what percent of a resource, because it's unitless and it allows us to compare the consumption of one resource to the next. So it's interesting to note that the sum over r prime is always less than or equal to r. And that's a useful thing to know as we're getting into the idea of a limiting reactant. So let's say we have 3 hydrogen atoms, and so those are all 3 H2. And then we have 1 oxygen atom, and I should say molecules, 3 hydrogen molecules and 1 oxygen molecule. So we have O2 here. So they react, and they form two waters, so that's 2 water molecules, H2O, and then we have 1 hydrogen remaining, so that's we have a limiting reactant in this reaction. We couldn't use every resource we have. We couldn't use all of our hydrogen resources or all of our oxygen resources. We have a limiting reactant. So H in this case, our headroom, is we have 2 oxygens, that's the maximum number of oxygens that we can take, and we have 6 hydrogens. That's the maximum number of hydrogen that we can use over the course of this reaction. R in this case, though, what we're actually using is 2 and 4, so that's 2 oxygens. We're only using 2 of those, and we're using 4 hydrogens. So instead of the 6. So we can see that oxygen is at 100% utilization. And oxygen, in this case, is our bottleneck. We still have more hydrogen to react. So in this case, we could have run out of memory, and we still have more CPU space. And then in that case, memory would be the problem for our application. That's our application's bottleneck. So let's talk about bottleneck detection. This is the good stuff. This is where we get into some interesting concepts. So first of all, we'll talk about required scope, and then we'll talk about throughput, because by defining throughput, we know when we're actually having a bottleneck. And then we'll talk about each of our resources, how to make them finite. So we need to define H, our headroom, which is the maximum value of all of our different resources. And that might not be completely obvious from some set of resources. Anyway, our required scope is global. So if you're looking at a distributed system and you're wondering what resource is bottlenecking you, then you need to be monitoring every resource on every box in that system. And that sounds astronomical, but with tools like Datadog or CloudWatch, monitoring becomes actually pretty easy, because you run an agent on the box and they report every last thing. So in practice, it doesn't really need to be global anyway, because an application only uses some subset of the resources of your entire distributed system. So essentially, you want to follow a path of a request from the load balancer all the way outside your system to the database on the other end, and then back out. So when we're talking about throughput, we need to choose some units, and the symbol for flow rate is usually Q. So we want Q in to equal Q out under normal circumstances. So the number of requests into your system should equal the number of requests coming out of your system. And the useful definition here of throughput and normal behavior is we don't have to worry about what's happening on the other end. So when you hit an API machine with a client request, your application request can fan out over different components of your infrastructure. And so one queue in can turn into 3 or more queue out. It's unbounded. It can be any value. So anyway, saying queue in equals queue out gives us some really realistic and predictable expectations that are really they adapt to your changing infrastructure. So under normal operation, queue in equals queue out. So during a bottleneck, that's not true anymore. And we're saying that a bottleneck is a resource that that's not true. We can't say that it's strictly less or strictly more, because sometimes it'll be less. Q in will be less than Q out, and sometimes your system will recover, and you'll see that Q in is more than Q out. So let's revisit our definition of a bottleneck. I said we weren't going to make a rigorous one earlier, but now we can, because we've got a little bit of the background. So a bottleneck is a resource that limits the throughput of a system such that Q in is greater than Q out. So we're sending more requests than we're getting back out. And I mentioned earlier it can go up and down. So for the sake of our definition, this is the average value of Q in and Q out over some smoothing window. So it takes into account some recovery. And your choice of what that window is it should be just related to the amount of time it takes your system to recover in between bursts. So if you have a sudden drop in memory consumption because your process crashes, and then you have a whole bunch of request timeouts at the gateway as a response, then your process will come back online, and you might see recovery as some of those requests that are hanging on the gateway they're served. But over the average of that outage, you're still going to see a drop in queue out versus queue in. So the maximum allocation of a resource allowed before queue in is greater than queue out is headroom. So that's the maximum allocation of a resource. And this is where we define those maximums. So this is an interesting idea. We have 16 gigs of RAM on the box. We have a 100% CPU utilization. But we don't want to go all the way up to 16 gigs or 100% because that can cause some major problems, and we'll actually see problems before those happen. At the time your process crashes because of a lack of memory, you'll have memory pressure. And one of the problems with memory pressure is you're overrunning your operating system's buffers and caches. So you'll see a degradation in performance before your operating system actively starts killing processes in terms of priority. In terms of CPU utilization, you'll also see degradation in performance. And so people choose a threshold around 70 or 80% to begin alerting so that they can intervene before that degradation becomes too significant. So headroom is that threshold at which we start alerting. We're not saying that it's the maximum number of resources on a box, but for our rigorous definition, we'll say it's the maximum allocation that we want to begin alerting at. So in terms of throughput and choosing units, our units of queue in and queue out are the number of client requests that are made versus the number that have not timed out. And in general, it's less. In general, we know that we have a bottleneck when that value is less than 1 over some average. Okay, so let's start talking about resources in particular. CPU is a complicated one. We have 10 different types of CPU that are monitored by our Linux operating system. Everyone's favorite Ubuntu. This is from my own host, and this is I forget what version of the Linux kernel I'm on, but these are pretty standard metrics that you'll find in /proc/stat on your file system. So if you want to cat /proc/stat, you'll see all these statistics, but they're not as nicely labeled. So user CPU is CPU time that's allocated to normal processes running in user space. So this is the CPU that your application will use, and it'll share with nice CPU processes. So you can change the nice number of a process, and this increments or decrements its priority in terms of the amount of CPU it's allocated under whichever fairness algorithm your machine is using. System CPU is the CPU used to execute kernel tasks. So anytime exec is called or something needs to be moved off of a peripheral device into memory, the system CPU will handle that. It services interrupt service requests and hard interrupts. Idle time is the time that you spend not doing anything. So there's you don't always need to be using your CPU. So sometimes it just doesn't have requests for any CPU cycles, and that's the period that your CPU spends in idle time, which is accounted for here. I/O wait time is a bit misleading. It's the time a task spends waiting for I/O. Your CPU isn't going to stop what it's doing and wait whenever you send a request to a network or some file handler. It's going to switch tasks and say, okay, what else can I do while we're waiting on this I/O? So I/O wait is the time a task spends waiting on I/O, not your CPU. So the guest metrics are all related to virtual machines, virtualization. If you're running Vagrant or VirtualBox, something like that, your guest CPU time, that's the CPU time that's spent in user processes on the guest VM. Steal is a pretty funny jab at the VM, I guess. This is the amount of time that your VM kernel is actually taking up your CPU on the host machine. So it's the operating system, from its perspective, is talking about another operating system stealing CPU away from it. I thought it was kind cute. So anyway, finally we have soft IRQ. These are software interop service requests. These are service requests like division errors bubbling up to the application layer, or exceptions, memory faults, things like that come from the operating system and then bubble back up to the to user space. And then interrupt service requests. So we have soft interrupt service requests. Those come from application space. And then interrupt service requests are similar to to software interrupt service requests, and that they trigger a context switch. So interrupt service requests come from hardware components. Whenever a network interface card needs to be read from, or a file handler is ready to be written to, like a socket, that'll cause an interrupt service request. So it alerts the operating system, hey, I have something that needs to be done at a hardware level. So let's talk about other resources. Network is a cool one. If you say ifconfig on your host, ifconfig right there, then you'll get some output like this, and this is what it looks like on my machines. And here I've blurred out the iNet, NetMask, broadcast, anything that's actually specific to my host, because I don't want to share all of my network information with you. But the components that are interested in determining usage and throughput bandwidth are these values here. So these values here. So RX packets, TX packets, these are the number of packets that have been sent and received, and then there's the number of bytes that have been sent and received. And they put it in a nice human-readable format so you can get some perspective on this. So ETH0 is my Ethernet port, that's my Ethernet card, and then LO is my loopback interface. And you can actually see that written down right here. So this one is what opens me up to the internet, and this one is local to my machine. So I've sent out 594 megs on my internet card. Sorry, I've received 594 megs, and I've transmitted only 27 here. Now, this is an interesting idea, and we'll get a little bit more into why this is interesting later when we talk about nonlinearity, but the transaction queue is a queue internal to the operating system where your process comes up with a packet, and then it writes it to a socket, and then that packet has to be broken up and put on a queue to be actually loaded into the network card and then sent out on the internet. And that queue has a length of 1,000. So these are 1,000 pointers to packets that need to be sent out to the internet. This is a cool trade-off because if you only have one packet on your transmission queue, then it'll have very little latency because it's the very first one to be sent out. At the same time, you won't be able to queue up very much, so your operating system will push back on user space and say, hey, I can't accept any more data right now, I'm not ready to be written to, and that'll limit your throughput up at the application layer. So having a long transaction queue, on the other hand, the 1,000th packet to be transmitted will see the latency of all of those other packets being loaded onto the interface at one time. So you're increasing your latency from the perspective of the kernel and decreasing it from the perspective of user space, because now you're able to load packets, you're able to spit packets out faster, but that queue backs up. And we'll talk about some consequences of that in a little bit. So something related to bottlenecks is error rates, and this is something that we'll kind of gloss over because presumably your application code itself erroring will not be the cause of your bottleneck, because hey, we don't push bad code out to production. There's lots of different types of memory, but there's only a few that are really specifically relevant to bottlenecks in most cases, and that's your total amount of memory available, and then the amount of memory that's in use. So you take your total amount of physical memory available, and then you subtract what's in use, and you have the amount of, you subtract what's free, and then you have the amount that's in use. So the free memory is the physical free memory. Memory available is stuff that can be evicted. So this one takes into account operating system caches and buffers. That's kind of an interesting thing to keep in mind and take into account. So when you run out of free memory, you're going to start seeing that degradation in performance because you're no longer getting optimal throughput on other things like page lookups and disk I/O. Speaking of disk I/O, if you use the df command or proc PID IO, you can get some stats like this. And this just says how much disk space is in use by your machine and how much is still available. So you can use this as a proxy to how much you're writing to your system. What rate you're writing data to your system. But there's you can also use some monitoring tool on Amazon, which I think we'll talk about in a little bit. There are other types of resources: locks and latches, application queues, network congestion, process idle time. These are things that are all measurable. You just have to find where you measure them. Locks and latches, for example, can be measured by show engine InnoDB status in MySQL. Application queues can be monitored in statsd at the application layer. Network congestion can be monitored on your cloud platform. Process idle time is the time your process spends sleeping and polling. That will relate to the idle time on your CPU. So we can also talk about process limits, and these are sort of nuanced things that result in bottlenecks, and they also require monitoring. You can only have a certain number of open files on an operating system. You can only have so much on the stack before you have a stack overflow. Only a certain number of processes can run on the operating system at one time. Only a maximum number of signals can be sitting in a queue waiting for the operating system to handle them before you receive some exception. So these are just example. This is just an example. These are the limits of the process 27181 on my operating system, and I found these limits by catting proc PID limits. And then finally, we'll talk about CPU, and I think we're almost done. So there's all these different metrics for CPU: user, nice, system, idle, I/O. We went over these earlier. These are the limits of it, and I get this from catting proc stat. So we're backwards. Here's network. So you can use iPerf to find your network performance, and this is a pretty good method. But you'll find that in a lot of cases you'll have a big, really high throughput before it drops off to some constant rate. You can also Google around. If you're on EC2s, you can look up your network throughput based on the instance size, and those are pretty reliable. So on my machine, I measured 2.27 gigabits per second using iPerf. It's really pretty simple to use. Your output kind of looks like this. And these are with some really default settings. So in terms of memory limits, mem total tells the story, and mem free is the other half of that story. In terms of disk I/O, Amazon will tell you. You can measure the rate from DF, but then if you want to actually know how much you get, the ops per second are on Amazon will tell you that. You can measure it on your machine, but it's right there if you're on a cloud platform. Okay, so now we get into the really good stuff. So we have ideas of what resources we have, how to measure some of them, and we can talk about the method for figuring out when you've got a bottleneck. So we've covered headroom and resources. We've covered the scope of monitoring. It needs to be everything that your application needs. And we've talked about where to find some of this information. Monitoring is really very solvable. So there are so many services that provide this for you. You probably have most of what you need right out of the box. So what we want to talk about, the most important concept we've covered is that we can put resources in terms of percentages of those resources. And having all of this context behind us, that's kind of what makes all this work. So we're primarily interested in seeing what happens as we increase QN. That's the number of client requests per second. So we can plot all of our resources as that happens, and we find these nice, interesting linear trends. We can use these curves to actually solve for the number of requests per second at which we see 100% utilization. So if from the equation over here on the left, if our CPU is equal to 0.0073 requests per second times requests per second plus 0.06, then our utilization at 100% CPU, if we let CPU equal to 100, we get 128 requests per second. So we know that our CPU will bottleneck at 128 requests per second. And we can extend this to all of our resources. We know from all of our resources, and you can automate this, we know from all of our resources that the maximum number of requests per second they can handle when their headroom when the resource utilization is equal to their headroom is 128 for CPU, 118 requests for memory, and then 1.11 million requests to be network bound. So as you can see, our limiting factor here, our limiting reactant, is in fact memory. And it's really hard to see these parts, this number on the left here, but this number on the left starts at about 80%. I over provisioned this box, so it's using a lot more memory than it really under provisioned this box, so it's using a lot more memory than it really should be, and that puts the limit at not all that much more headroom from where it is. And we get a little bit more information out of these equations than what might meet the eye. We can actually get the idle statistics on the CPU by looking at these. So our CPUs, not just the CPU, but in all of our other resources. So when the box is sitting there, when the request per second is at 0, our utilization is at 0.05% CPU, and that's about right for a CPU that's idling. This guy has an agent running on it, so it's slightly more than 0, and this will give you the baseline. You don't even need requests per second to go all the way down to 0 to get this, because we're fitting it. So just as we can predict what happens on the right half of the line, we can predict what happens on the left half. So we know that we know what our baseline is. And in this case, you can see that our memory footprint, our memory baseline is 87%. So we only really have 13 before our box is totally full. So that's why our memory utilization is our bottleneck. Now, before we scale, before we re-provision, we need to take into account a couple of things. The first of those is downstream impact. We see that here the maximum requests per second that we can handle with our system as it stands is 118 requests per second, which is really not that much. Now, if we provision that so that we can handle 1.11 million requests per second like we can for our network, then we're going to have a real problem because our CPU can only handle 128. If we provision both of these so that they can handle 1.11 million, then we probably can handle more load than we'll ever see. So we know in this case that we've got it handled, but we have to think about what happens when our CPU goes up to 100%. If we're expecting our load to be greater than 128 requests per second, and that's really pretty close to 118, then we need to expect our CPU to get up to eat up it all the way up to its headroom. So when that happens, really bad things happen. It can take so long to process requests that requests back up, and it can have this cascading effect. Heartbeats start to get missed and really bad stuff like that. So by provisioning more memory, we can in fact take down systems with these unintended consequences. You can imagine if it was the other way around, we provisioned more CPU and now our memory is the limiting agent, our processor would start getting killed by the operating system, and that's a really bad problem to have. Now, the last thing I wanted to talk about is a reference back to that transmission queue that we saw on our Ethernet port. And this is nonlinearity. So when you have a packet that's sitting on that queue, there's going to be some amount of time to process it based on where it sits in that queue. So as the time to process it increases, it's going to take more time to process each packet because that's the link that you have left. So the packets taking longer cause more packets to be added, and the growth of that queue is exponential. And that goes for any queue. Queues are a-holes. So application queues, the queue on your app server. These are all things that you need to take these factors into account for. They don't become a problem if you make the appropriate choice of headroom. So if you keep your headroom low, then you can intervene before you have to worry about these nonlinear effects. Things only get backed up on there when you're having other issues downstream. And that's about it. So thanks for joining, and I hope to catch you at one of the meetups over here in New York. Take care.